Welcome to The Explainer. I'm so glad you're here today because, well, we're going to completely shatter a pretty persistent illusion. When most of us think about artificial intelligence, we picture something weightless. We imagine invisible code, ethereal algorithms, data just floating seamlessly up there in the cloud. But what if I told you that AI is actually incredibly heavy? Today, we're diving into a fascinating report from the Alan Turing Institute, and we're going to uncover the massive hidden physical costs of resilient defense AI. We're looking at exactly why, especially in the high-stakes world of military operations, software comes with some very, very intense physical realities.
Let's totally reframe how we view machine learning with just one number, 50 gigawatt hours. According to the research, training just a single large-scale AI model can consume more than 50 gigawatt hours of energy. To really put that into perspective, that's literally the equivalent of the annual power consumption of thousands of everyday households. Just think about that for a second. It's a staggering reality. We aren't talking about a few laptops quietly crunching numbers in a back room. We are talking about industrial-scale energy consumption just to get one single AI model off the ground. And the thing is, that individual energy cost, it scales aggressively. If current exponential trajectories hold up, AI and its related infrastructure could reach 72 terawatt hours by 2030. That is more than 1/4 of the United Kingdom's total power consumption back in 2021. Yeah, you heard that right. One single tech sector potentially devouring 25% of a nation's entire power grid. It immediately makes you realize that scaling AI isn't just some software engineering hurdle. It's a massive, profound infrastructure and resource challenge. So this is the true essence of what the cloud actually looks like. It's definitely not just vapor floating in the sky. It is a massive, physically tangled, and incredibly energy-hungry hardware reality. We're talking miles of copper, silicon, highly complex supply chains, specialized cooling systems, and these just vast, sprawling data centers. When we talk about AI sustainability, what we're really talking about is the long-term viability of securing the physical resources you actually need to keep these tangled webs of infrastructure running.
Moving into Section 1, Military AI in Reality and what the actual stakes are.
You see, in the commercial world, an energy-hungry AI model really just means a super expensive electricity bill, or maybe a hit to a company's carbon footprint. But out in military operations, energy is a critical vulnerability. The environment is degraded, supply chains are constantly contested, and resources are finite. We literally have to weigh the perceived software benefits of AI, things like algorithmic performance, unprecedented speed, and that critical informational advantage, directly against its intense material constraints and the massive logistics burden it brings. A lot of the policy discussion out there focuses solely on the benefits, right? But treating the energy demand and material intensity like they're just secondary concerns, that completely ignores what actually shapes combat power.
So here is the absolute crucial point. Energy equals combat power. Imagine deploying an incredibly advanced AI system to the front line. It offers amazing situational awareness, but it requires a massive, incredibly loud, heat-emitting diesel generator just to run its servers. Or think about an AI-driven wearable device that drains a soldier's battery in an hour. In those scenarios, the AI isn't a tactical advantage anymore. It's a huge liability. It creates this massive logistics tail, requires way more fuel convoys, and potentially even exposes your position to the enemy.
Which brings us to our next section, deconstructing the threat through the AI system stack. To really wrap our heads around how deep this vulnerability goes, the report adapts Benjamin Bratton's concept of the stack. It's basically a way to logically break down these incredibly complex, interdependent layers of AI vulnerability, because we can't just look at the software in isolation. We have to look at the whole vertical system, top to bottom. Actually, scratch that, bottom to top. At the very bottom, we have the Earth layer. That's the raw materials, critical minerals, and sheer energy required. Above that is the cloud, the data centers and platforms. Then infrastructure, how the AI is actually deployed out to bases or into the field. After that, the interface, the human-machine interaction, especially out there in degraded conditions. Above that is the user, their training, their behavior. And finally, governance, the policies managing all these strategic dependencies. The real genius of this model is that it shows how a constraint at that raw material Earth level propagates all the way up the chain, ultimately impacting governance and the viability of the entire system.
All right, let's look at Section 3, deploying on the front line.
So how do all those abstract layers actually translate to the mud and grit of the real world? Well, we can break this down into 3 distinct deployment models to see exactly how these energy problems manifest in combat scenarios. First up, you've got the cloud-based homeland model, which is typically used for heavy intelligence analytics. Now, it benefits from grid energy and massive scale, sure,
but it depends entirely on centralized, highly energy-intensive installations. Second is the edge-based behind-the-frontline model. Think of an electronic intelligence node. This relies on vehicle power or portable generators, which creates a direct trade-off between responsiveness and adding new demands onto fuel logistics. And finally, edge-based frontline wearables. Here, you've traded grid power for strict, unforgiving battery constraints. That energy is a direct limiter of a soldier's endurance and survivability. Every single one of these deployment models carries its own specific physical trade-offs.
Now, the good news here is that leadership is definitely waking up to this reality. Organizations like the UK Defence AI Centre, or DIAC, who actually commissioned this research, recognize that sustainability and resilience can't just be treated as bolted-on afterthoughts. Resource consumption and cooling requirements, they have to be managed from the very conception of a system, all the way through to its procurement and its final deployment. You simply have to design these capabilities with those constraints in mind right from day one.
Let's move to Section 4, the rebuild, building resilient AI.
Because listen, this isn't just about identifying vulnerabilities and throwing our hands up. It's about engineering our way out of them. How can defense forces actually become more lethal and more resilient by tackling these resource constraints head-on? Well, the answer lies in concepts like lean AI and green AI. There's this growing body of scientifically backed methods designed to optimize capability without relying on massive, vulnerable infrastructure. Lean AI refers to things like small language models. So instead of relying on a massive cloud-based model that requires gigawatts of power, you use a highly specialized, much smaller model that can run locally. That optimizes the compute and drastically reduces the resource drain. Because let's be honest, you don't always need a sledgehammer to crack a nut, right?
And the data on these energy reduction techniques is honestly incredibly exciting. Just by processing data locally using Edge AI, studies are showing you can cut energy consumption by a massive 40%. Then you have techniques like quantization, which is a big word, but it basically just means reducing the precision of the numbers the neural network uses so it's smaller and more efficient, and that can cut energy by 30%. And pruning, which is literally just removing redundant parameters from the model entirely, cuts another 25%. We can drastically cut computational and memory costs without actually compromising on the model's accuracy and performance. It's a real game changer.
We also have real-world blueprints for this exact kind of resilience. The report highlights some really powerful lessons drawn from Ukraine's response to sustained attacks on its infrastructure. So what did they do? Well, 1, they accelerated energy innovation out of sheer necessity. 2, they established comprehensive emergency and business continuity plans. And 3, absolutely crucially, they decentralized and distributed their data centers. It's a completely proven roadmap for maintaining AI operations and digital infrastructure even in severely degraded conditions.
This entire paradigm shift we're talking about is perfectly encapsulated by one specific line in the report. It reads, "Energy management functions as a determinant of combat power and is not simply an environmental concern." That really hits the nail on the head. We aren't talking about going green just for the sake of it or for good PR. We are talking about operational survival, tactical lethality, and ensuring your systems actually work when you need them the absolute most. Which brings us to our final thought for today. We've seen the massive energy demands, the tangled physical infrastructure, and the immense logistical burdens that come with deploying AI. But we've also seen the path forward through lean models and decentralized systems. All of this, though, forces us to ask a really critical question. Are our current tech ambitions truly sustainable on the battlefield? It's a question that demands a very honest answer before the next generation of defense technology is deployed. Thank you so much for joining me on this explainer. Keep questioning the physical reality behind the software, and I'll catch you next time.